and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
It's true, and I count myself among those. Less overwhelmed than I was probably a year ago. But I'm Corinne Caputo, a writer and a funny person and a friend of the universe.
Yay! I'm so glad to hear you are less overwhelmed than you were a year ago by the universe.
I think if I were to look it in the eye, look the universe in the eye, I would still be very scared. But the existential dread is certainly going down. Although I guess it's the same.
I like to hear that. Hello, everyone. I am Dr. Moiya McTier. I'm an astrophysicist, a folklorist, a friend to the universe, and today, if you're listening to it on the day that the episode comes out, I'm the birthday girl!
Yay! Happy birthday, Moiya.
I love my birthday so much. Thank you, Corinne.
I'm so glad to hear that. What are you going to do for your birthday?
I am in New Orleans for an astronomy conference.
Of course you are. Yes.
The biggest astronomy conference in the world every year. And I'm really excited about that, to see all my friends and get an update on what people have been doing in the field of astronomy over the last year. So look out for some episodes coming up in a few weeks, because we're going to be doing some episodes about this conference.
That's a great idea. I love that.
But we recorded this episode. Under a massive orrery. Corinne, do you know what an orrery is?
Yes.
Can you say the word orrery? Because I don't know if I can correctly.
Orrery. I feel like I get tongue-tied a bit. Orrery.
Yeah.
Yes, it's kind of, I don't know if it is out of date or what, but it's kind of an aesthetically old-fashioned solar system, right? Model.
Yeah, it's a model of any sort of celestial system, typically the solar system with the sun and the planets orbiting around it. And it does have that very steam or cyberpunk vibe to it. Although
yes, exactly. I was going to say, I feel like I've always seen it in a set piece in the background of a movie or something. Probably in some wizard's office in any number of fantasy movies.
Oh my god, yes. They always have an orrery. You're so right. And sometimes they're the really small ones on their desk.
Yeah.
Yeah, and then they have the big ones that move on their own. We are under one that is like the orrery from Tomb Raider. So it's lots of gears. We can hear the gears shifting, but definitely less of an ominous and insidious vibe than the orrery in Tomb Raider.
Totally.
Yeah, this is a friendly, peaceful orrery. And it's just really nice to be able to look up and see the motions of everything. It is to scale in terms of their relative periods, but it is definitely not to scale in terms of their relative sizes and distances from each other, because you can't do that. You can get the sizes of the bodies relative to each other, but then you can't get the distance between them, or you can get the distance, but then the bodies themselves would have to be so small that you couldn't really do the scale there. So we are sitting here under this orrery watching the bodies move above us, because today we're going to be discussing the laws of motion in the universe. Yay! What comes to mind, Corinne, when you hear laws of motion?
I think of school. I think of elementary school, and I feel like it was one of the more complicated science things you learn. Not even that it's complicated, but just that there is a greater kind of level of existence happening that scientists have put words to.
Yeah, learning about gravity is kind of trippy because it's a weird concept, and our society's understanding of it has changed over time, but you really have to introduce it slowly. So when you said elementary school, in my head I was like, wow, that's really early to be talking about these laws, but I guess conceptually the idea of gravity being a thing,
it was probably middle school where I learned it, but I think I probably had more fondness for my elementary school science class.
Yeah, that was before the teacher who denied the moon landing.
Yes, exactly.
I probably heard about Kepler's or Newton's laws. I'd heard about Newton's laws in high school. I remember that for sure. Kepler's laws I may have heard about, but I didn't understand them or the connection between the two probably until college, which is when I really got into physics and took my first real physics class.
Yeah.
But there are, I'd say, 3 people whose work really contributed to shifting our understanding of motion and gravity. One of them is the person who gave us the concept of gravity. So we're going to be talking about that one. I'm sure you can figure out which one it is.
We'll see.
Who do you think? Who gave us gravity, Corinne?
That was Newton.
That was Newton. Yes. So we'll talk about Newton. Kepler's laws, I got very familiar with when I was studying exoplanets in college and grad school. And then we got to talk about our buddy Einstein, who then completely revolutionized the idea of gravity in universal scales. So we're going to start at the beginning with Kepler. Johannes Kepler is his name. He was born in Germany in 1571. The church is still very strong at this point. Copernicus has done his revolutionary theory, so the idea of a heliocentric system is out there, and you'll see that it influenced Kepler for sure. But people are still wary of that, and there are a lot of parts of the world where if you say the Earth isn't the center of the universe, you will be called a heretic, and you probably won't be sentenced to death. The church stopped doing that in earlier in the 1400s and 1500s, but you might get run out of your town.
Sure.
Which is kind of what happened to Kepler. So let's get into his life, because we're not going to do a whole bio episode on Johannes Kepler. We probably will do one on Einstein, but I'll give you some brief info here. 1571 in Germany. He was interested in astronomy from a young age because his parents took him to see some astronomical events. There was a comet that passed by, so he would have seen it as a shooting star, but they would have known by then what comets are. Throwback to our Caroline Herschel episode. He also saw a lunar eclipse. His mom took him to see a lunar eclipse, and he was like, "Oh, this is so cool." Not a direct quote, but, a quote in vibes, in energy. He was interested in Copernicus's work. Nicholas Copernicus was the guy who really, I think, did the brunt of the work, toppling the geocentric model and saying that the sun was at the center of the planets. And Johannes Kepler, who I shortened to JK in the notes, so it might make me giggle a few times. Johannes Kepler's first astronomy publication was called Mysterium Cosmographicum, which is a cosmographic mystery, and he published that in 1596. He was at a university at the time, and it was the first published defense of Copernicus's heliocentric system. But it did include some very complicated models for the universe that had different levels of polygon shapes to account for the observed motions of bodies. So previously, people were like, the Earth is at the center, and then there's a sphere of celestial bodies that move. These are the wandering stars, the sun, the moon, and the other planets that we can see. And then beyond that, there's the sphere of fixed stars. And all of those objects were fixed in their sphere, and the sphere rotated around the Earth. And so there was this model that people had at the time of concentric regions that all rotate independent of each other and house different objects in the universe. Kepler kept that, but turned it into these different polygon shapes, and he was trying to base it on the observations of the body's motions, because sometimes planets are in retrograde, sometimes they move faster. It's just weird stuff is happening, so clearly our model is wrong. Kepler was very religious. And it didn't seem like he was trying to keep with this concentric model just to appease the church. It seemed like it was really something he believed. In his Mysterium Cosmographicum, he described the sun as something that represented, literally represented God the Father. And then the stellar sphere was the sun. And then there was another sphere that, the space between them represented the Holy Ghost. And so he really mapped space and his idea of the cosmos onto his theological understanding of the universe. There was a one-to-one match for him. That paper also included an early attempt at an equation to relate a planet's distance from the sun and its orbital period. And it does sound kind of obvious now that there should be some relationship between how far away you are from something and how fast you're moving around it. It was not at all obvious at the time. Not at all. But like they had seen chariot races. They had tracks that people ran on. They understood that if you're on the outside, it takes you longer to go around.
Yeah. I always think about that too. I'm like, how far would I be right now if someone hadn't literally told me what was going on? If I had to figure it, like, if I had to put words to it, I get it.
Yeah. And when we tell the stories of these discoveries, it does kind of seem like they just came up with it out of nothing.
Right.
But that's because we don't have enough time to dig into the nuance. He went to school. He learned from people who had been, like, engulfed in these ways of thinking for decades. He was a revolutionary figure, but that's because he put the last straw on the pile.
Yes,
you know, he didn't build the whole pile. He just put the last one on. Let's see. So he publishes the Mysterium Cosmographicum. He then starts working as an apprentice to Tycho Brahe, who we have talked about very briefly on the show before. Let's see. He was a Dutch astronomer, I think, and he had his own observatory. But this is a time before telescopes were invented. We didn't start looking at space with telescopes until 1610. So Tycho had an observatory, but it didn't have a telescope in it. It had like sextants and like quadrants and other tools that you could use with your eyes to try and precisely map the locations of things you could see. And then he was just taking very meticulous notes about where things were over time. With those notes, Kepler was able to actually track the motion of planetary bodies around the sun, and for the first time actually like get an idea of the shape of it, because we were just assuming that these bodies orbited in perfect circles because the Greeks decided that the circle was the perfect shape, and then everything in the universe must be a perfect circle.
I have to agree.
Yeah, it's pretty good.
I feel like it's the one shape I'll never be able to draw.
And that makes it perfect? I feel like that makes it the worst shape.
That makes it perfect. Unattainable.
Okay.
No.
Okay. This is the corner where Corinne and Moiya talk about the philosophy of perfection.
And my relationship with it.
Yes. Must something be unattainable to be perfect?
Yes. To be loved.
Oh, that's a little too deep.
It's our other podcast.
So Kepler is taking these observations that Tycho has done and that he has helped Tycho do, and he comes up with the idea of a non-circular orbit. And he actually does come up with the idea, the concept of an orbit instead of these planets that are fixed in that rigid rotating shell. Instead, it is the planets that are moving through some ethereal medium.
Sure.
Yeah. And Kepler does a lot while he's working with Tycho. He observes a supernova in 1604, which was the last supernova observed to happen in the Milky Way galaxy. And he wasn't the first person to observe it. People saw it a couple of weeks before he did. But he wrote about it so extensively that we named it after him. So he now has the Kepler supernova from 1604 named after him because he wrote about it in his book in 1606, De Stella Nova, the new star.
That feels like a screen name or something that I would pick.
You still can't.
You're so right.
Okay, so then he starts studying the orbits. He introduces the concept of the orbit, and going back to his idea that the sun literally represented God the Father, he attributed the whatever force that was moving those planets to the sun. So he was like, there is this mystical force connecting, like a string connecting each planet to the sun, because that's where God is, and God is attracting everything to him. And he called it, or he didn't call it gravity, but it was what gravity ended up being. He then came up with his two laws. The first laws of motion, he didn't give them numbers. We assigned those later. He came up first with the second law, and then the first law, and then the third law was formalized. But the third law actually was one of the first things he came up with. So it's all very confusing. But the first two laws were published in a paper or book called Astronomia Nova, New Astronomy, in 1609. And the first of those laws is as follows. Planets follow an elliptical path around the sun, and the center of the sun is at one focus of the ellipse. The other focus would be somewhere else. But most importantly, this first law says that the motion of planets around the sun, the orbits of these planets, are not perfect circles or even epicycles, as some ancient Greek philosophers tried to describe to explain retrograde motion, but they were instead ellipses, so ovals. And Kepler even dismissed ovals for a long time, or ellipses for a long time. He was trying parabolas, he was trying some weird egg-shaped orbit, because he was like, ancient people who came before me certainly wouldn't have dismissed the oval so easily if it were a good option.
Sure.
So friends, this is your reminder. Like, even if it seems like a silly idea, test it out. Because Kepler would have figured out elliptical orbits a lot sooner if he hadn't just assumed that the people who came before him knew what they were doing.
Yeah. Yeah, don't think everyone else is smarter than you. This is what I'm dealing with.
Yeah, so always test it out. Corinne, is there anything that you have ever like dismissed as a silly possibility, and then later you realized, oh, if I had just done that first?
Oh, literally every time I'm pitching ideas at work or something, I'm always just like, whatever the simple thing I think of, I'm like, there's no way that would ever work. And then like that'll come up in the meeting and I'm like, wait, I thought of that. Like I just for some reason have decided the things I'm capable of thinking of are not enough, if that makes sense. And then I end up overworking an idea.
Corinne, you are enough.
I am enough. And I just need a good night's sleep, and I'll be back.
Don't we all?
But this is a good reminder of like some of the foundational knowledge of our universe was you just got to be confident.
Yes, be confident, but test.
Yes, I like that.
Test to confirm.
Test to confirm.
Like, I know I'm right, but this is the evidence to show other people that I'm right.
Yes, exactly.
All right, so that is Kepler's first law, published in Astronomia Nova. And then he also included his second law, which is that an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time. Does that explanation make sense intuitively to you?
I don't think so.
Yeah, I agree. Another way of saying this is that planets move faster when they are closer to the sun and slower when they are farther away.
Okay, that I understand.
Yes. Here's another lesson. I think this one in communicating complex ideas, because one of those is way more intuitive, at least in my opinion. And I'm sure there are people for whom the geometry thing is more intuitive, if they tend to think more in like geometrical or shape-based terms. Originally, Kepler's hypothesis was the second thing that I said. It was that planets are faster when they're closer to their stars, but the math to prove that was really hard. At all of the points of his observations for the location of, it was Mars specifically that he was using, Mars around the sun, he would have had to measure or calculate its velocity and its precise position at every point, and that's just really difficult to do. The geometry-based way of proving that was a lot easier. He just drew the ellipse and then drew slices of the oval pie, and then measured the area of all of those slices, and that was a lot easier to prove because you could do it over longer periods of time, and you didn't need such precise, discrete pieces of information.
Sure.
And so he ended up proving it in the geometry fashion and then wrote the law in the geometry language, and that to me is less confusing.
Yeah.
So just a reminder that there are always different ways to approach a problem, and some of them will be easier for you to intuit or wrap your mind around, and others will be more difficult, and it's just a matter of finding whichever approach is easiest for you to understand.
I love that. I did not know that when I was a kid in school. It was always just this is how you have to learn something, and when it didn't work, it was my failure.
Ugh, they love to make the students feel like it's their failure.
Yeah.
Absolutely not. And it's most of the time it's not even the teacher's failure. Actually,
it's
right?
not even the teacher's failure. It's just for my classes especially, it was there's 35 kids in this room. We're not we don't all have the same brain.
And like teachers don't have total control over what they show or how they teach it.
Oh, yeah. And I think it was just me giving myself permission to learn something in a way that resonated. I feel like I didn't know that was a possibility for a while.
Yeah, because people talk about the learning styles, and I think that's been debunked since, like, the whole visual versus, like, kinesthetic learner thing.
I believe that.
I mean, I don't know. I'm not that type of scientist, but people talk about that, and that's important. But you also have to think of, like, even within someone who is better at reading information instead of listening to it, like, the way things are phrased is also very important.
Exactly. And I think that's what was thrilling to learn of, like, oh, when it's explained in a different way. I mean, we've talked about Carl Sagan or any kind of sci-com, like, influencer even online. And it's all, you find your person and you learn cool stuff.
Yes. So it's the same thing said a couple of ways. Planets move faster close to their stars than they do when they're further away. And because the orbits are ellipses, there are times when the planet is closer and further away from the star.
Makes sense.
The third law was published in 1619 in his Harmonices Mundi, although he had been, like, working around it for a long time. This is just when it was first officially published, especially in equation or formula form. But this rule is that the squares of the sidereal periods of the planets are directly proportional to the cubes of their mean distances from the sun. And I honestly think this is rare, but I think that it's actually easier to understand that in equation form. It is that the period of the planet squared is proportional to the radius of the planet's orbit cubed.
Okay.
Yeah. Proportional to. That's very important because he didn't have, like, an actual equation. There were other constant values that he didn't have, but he could map out the proportionality. He would not be able to apply this to any other stellar system because this is based on, it depends, the actual equation depends on the mass of the star and also the mass of the planet doing the orbiting. And on a gravitational constant, which we didn't know until Isaac Newton did his thing. So that's what we're going to talk about next.
Cool.
Hey friends, Moiya here. Corinne is surfing on the rings of Saturn as it goes around this orrery. Corinne, please be careful. Please don't fall. But while she's up there, I figured now would be a good time to thank our patrons who support the show every single month. Thank you so much to our sun-like stars, Sharn Llewellyn, Lissa, Scott Reynolds, Ian O'Leary, and our latest sun-like star, Tom T. As suns, I did the math, your gravitational pull is almost 30 times stronger than Earth's, making you all the most attractive beings in the solar system. So I hope you enjoy that. You too can support us. You can hear your name on the show, and you can make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. And we are now offering annual memberships. So if you sign up for a whole year up front, you end up getting a 13% discount across the entire year. That is 1% for every constellation along the ecliptic, which is the path that the sun appears to take in our sky over the course of a year. You can find the star chart, our Patreon info, and more at our website, palebluepod.com, or go right to patreon.com/palebluepod. And if you can't support us financially, we totally understand. That's fine. You're still space. You're still a part of the universe, so it still loves you. There are other ways to support podcasts like ours. You can rate and review the show on whatever app you use. I really love reading every single review we get. You can also share the show with your friends because word of mouth recommendations are especially powerful in helping a show grow. And we would appreciate any way that you can help us get Pale Blue Pod into more ears. I'd also like to recommend another show on the Multitude Collective. It's called Spirits. It's actually one of my personal favorite podcasts. I listen to it every week. Spirits is a history and comedy podcast focused on everything folklore, mythology, and the occult, and it's told through a lens of feminism, queerness, and modern adulthood. The two hosts are mythology buff Julia Schaffini and her childhood best friend Amanda McLaughlin. Together, they learn about a different story from mythology and folklore are from around the world over drinks. And that's everything from mythological origins of major franchises like Lord of the Rings and Wonder Woman to modern urban legends that they get from real listeners so you can hear your hometown urban legend read on the show. They also do like roundup of werewolf and vampire stories from around the world. They've done Pokemon episodes. They've done episodes on some of the most obscure folklore figures you have never heard of. So you can start listening to Spirits now. They have more than 350 episodes. They are quite impressive. They've been doing this for over 7 years. So they have a huge catalog that you can go through and enjoy, whether you're here for analyses of mental health and mythology or creepy modern ghost stories. Dive in at spiritspodcast.com or search for Spirits wherever you download your podcasts. And of course, if you don't want to type anything in, the link to the Spirits website is down in this episode's description. All right, Corinne safely got down from the rings of Saturn. She's getting back, so let's get back to this episode. Johannes Kepler died in 1630, and then 12 years later, Isaac Newton was born in England. So if Kepler explained how the planets moved, then Newton explained why. And it was because of gravity.
Cool. I, for some reason, did not realize he was English. I don't know what I thought Newton was.
Maybe Italian?
Yeah, I think I thought Irish for some reason.
I think I always thought he was Italian because in my mind, this story, this legend that we have of Newton having the apple fall on his head, which by the way probably like isn't real.
Yeah, but that is a very English image. I'm surprised I didn't picture like the English countryside.
Actually, in my head, when I've always imagined it, for some reason, the Tower of Pisa is in the background.
Oh, that's so funny. That's so funny. Definitely my Staten Island roots are like, that's not an Italian last name. Like, Newtoni.
Newtoni. Isaac Newtoni. So there is that legend, which is almost completely not true, of Isaac Newton observing an apple falling from a tree, which supposedly happened in 1666, and then being like, oh, gravity.
Yeah.
You know, like there's definitely a lot more wrapped up into this.
Which is definitely how I wish ideas to come to me.
I know.
I'm like, it's just going to happen. I'm just going to see it.
Mm-hmm. And then everything will click and you'll have that pure eureka moment.
Exactly.
Mm-hmm, that would be nice, but it so rarely actually happens like that. I think he was in school at the time and he was like working on other things. But whatever that first incident was that made Isaac Newton think of gravity, he started to really think about falling in different contexts. He was thinking about apples falling to the surface of the earth. He was thinking about the moon moving around Earth. He was also thinking about Kepler's work looking at Mars moving around the sun, and he started realizing that all of this motion is caused by similar forces. He writes, "To the same natural effects we must, as far as possible, assign the same causes." So basically all motion follows the same rule, and the thing that is causing it is something that I'm going to call gravity. Why not? And so he started applying Kepler's laws to the motion of the moon around Earth, saw that they matched up, yay, and then conjectured that this thing called gravity connected the moon to the Earth and also was that same thing that connected all other bodies. And so he publishes in 1687 his like magnum opus, his grand career work, and it's called Philosophiae Naturalis Principia Mathematica.
Now that's Italian.
Yeah, it's like Latin or Italian. And it means the mathematical principles of natural philosophy. He publishes this in 1687, and it has his 3 laws of motion, plus a fourth universally important law called the law of universal gravitation. This says that any 2 bodies that have mass are going to be attracted to each other by a force that is proportional to their masses and inversely proportional to their separation squared. There's a formula that goes with it. It's that F is big M, little m over r squared, and there's a big G in there. If you are familiar with physics equations in these days, in like the modern day, there's a big constant g that's supposed to be in that equation for gravitational force. That is the gravitational constant, and Newton himself didn't calculate it. He left all of his equations as proportionalities, and then someone later calculated it, and it's what we use today. So thank you. I have to look up the gravitational constant every single time I want to do an equation for gravitational force. I could never remember what it is. It's like 6 something times 10 to the negative 11, but that's with very specific units like meters per second per kilogram square. I don't know.
I'm like, what if I knew this? What if this I knew?
That would be great. Even in my...
Okay, wait, Moiya, pretend to close your ears. Listeners, I need to study something. And then in an episode weeks from now, I surprise Moiya by knowing everything. Okay, Moiya, you can come back.
Oh, I wonder what you just said. I'm so curious to see what the outcome of that is going to be. All right, so he has his law of universal gravitation in Principia. People usually just shorten that long title to Principia. And then he has his 3 laws of motion, which I learned in high school physics, and I think other people probably learned in high school physics. The first is the law of inertia. Does that ring a bell?
Yes, that I know. Or okay. I think I know.
Do you think you could say the law of inertia?
I think that it is... objects in motion stay in motion. And I don't know like what the kind of written language is for the rest of it, but it's like an object in motion will stay in motion unless like it is stopped.
Yes.
And an object at rest stays at rest unless it is moved.
Yes. That's it. Yes.
Okay, listeners, forget the plan. I did it.
What? There's a plan? What's this plan? Oh no. Yes, that is the law of inertia. An object in motion will tend to stay in motion, and an object at rest will tend to stay at rest unless they are acted on by an external force.
Okay.
I also love the language of this, that they tend to stay in motion. They tend to stay at rest. I just love that Isaac Newton has left in this little possibility of like, it could just move on its own.
Yeah.
Why not?
Why not?
Why not? He's not trying to go for absolutes here. So that's rule number 1. Law number 2, it is a very famous equation.
It's about force and like equal and opposite.
That's
I don't know the wording. Oh, okay, then I don't know.
Okay. Well, the third one, now that you've got it, is that for every force applied, there is an equal force applied in the opposite direction. This is like, for any action, there is an equal and opposite reaction. Newton himself said, if you press a stone with your finger, the finger is also pressed by the stone, which I think is just like a cooler way of saying it.
Thinking about it.
It feels very like ancient proverb.
Yes, exactly. Like somehow I would get that in like a tea bag. It would be like on the tag of it or something.
And you'd be like, oh my God, yes.
Yeah, I think you're
You're
right.
so wise. So that's the third law. The second law is F equals ma, which is the first equation I memorized in physics. And if you can memorize that equation and you're really good with a tool or a process called dimensional analysis, where you can basically figure out what equations are based on the units of your factors in the equation, you can get from F equals ma to so many other important equations in physics. You can get to the force of gravity equation from physics. You can get to the potential gravitational energy from this. It's so cool, so useful to any physics or astronomy students out there.
Sure.
Definitely learn your basic equations and learn dimensional analysis. That is my advice. In words, that law says that the rate of change of momentum is proportional to the net force acting on it. And it says momentum because momentum is mass times velocity, and the rate of change of velocity is acceleration. So your mass times acceleration is going to be proportional to the force acting on it to cause that acceleration.
Sure.
Yeah. Basically, it takes more force to move a heavier object.
Yeah.
Newton published that and then made it kind of clear that he was uncomfortable with the way that gravity lets bodies influence each other at a distance through a vacuum medium. So he came up with this idea of gravity, and he was like, there are these invisible lines. But he didn't quite have Kepler's thing of believing that it was God doing the pulling on that string. And he didn't know about gravitational waves. He didn't know about quantum particles. So he was like, I see this thing, but I don't know how it works, and I'm uncomfortable that it can work across large distances almost instantaneously. That's an issue. So then we get Einstein, who comes in and he adds his theory of relativity, he adds relativistic effects, he adds reference frames, and really kind of ties together these like different realms of scale, where for Kepler and Newton, they were only observing things on smaller scales. They didn't even know that we were in a galaxy. And their idea of gravity worked really well for like solar systems, but not necessarily as well for bigger and also like smaller things. So Einstein came in and helped. We're most likely going to do a whole episode on Einstein because we have enough information about him. But he was born in Germany in 1879, and in 1905, while he was working at the Swiss Patent Office, he published 4 major papers. One of them was his theory of special relativity. It actually wasn't called special relativity at the time. I think it was just called like his theory of relativity, and then after he did general relativity, he renamed it. But this paper on relativity came about because observations of how light or electromagnetism behave weren't matching up when you observe them in different reference frames. So if you were like if you were on a train, Einstein's like classic thought experiment. If you are on a train going one direction and someone else is on a different train going in the opposite direction, there are differences in your perception of that experience. And so Einstein added into laws of motion the idea of a reference frame, which really is just adding in the idea of relative perspective, like seeing things from your point of view and knowing that your position and your time and your motion will influence you, like how you experience something. And so Einstein's idea is that the laws of physics are the same everywhere, but your observation of a different reference frame will be warped. And the only thing that is constant in the universe is the speed of light in a vacuum. And you can use that, plus some other very cool math equations that were developed kind of around the same time or just before. You can use those two things to transfer from one reference frame to another. And those mathematical equations are called Lorentz transformations. They were developed completely separately, and many people also came up with these independently, but then they were named after someone called Lorentz, which often happens. And those Lorentz transformations show that things that we think of as constant, like mass or time or like the length of something, those are actually not constant. And if you are moving with any sort of velocity, those things change. So as you get closer to the speed of light, you develop these Lorentz relativistic effects where your mass decreases, time gets weird, and I think I can't remember if you get stretched out or if you like get really tiny, but your size does change if you move super fast.
Ooh, I'm trying to remember. I feel like I saw a video where they kind of did some kind of graphic illustration of what that might be like.
I'll look for it in the research notes.
Would you rather be really tiny or really stretched out?
I would rather be really tiny. Oh.
In space?
Oh, in space, I would rather be really stretched out.
Yeah.
But on Earth, I would rather be really tiny.
I completely agree.
Yeah, because I feel like there are very interesting things to explore at the tiny scale here on Earth.
Oh my God, I've been wishing for that my whole life.
Yeah, like Magic School Bus has just given me that dream of shrinking down.
I could live in the dollhouse that I made.
Yes.
Already is my dream aesthetic.
You could fly into the squirrels' heads and like work inside their brain.
They might eat me.
No, just go right to the brain. Go through the ear canal.
I think being tiny would be a dream come true.
But in space, everything is so big. You have to be big.
I know. But I'm like, how big
anything.
would I be to even feel normal sized?
Oh, I feel like people have done this calculation. Because in my head, I'm like, the longest you could be is all of your atoms lined up back to back.
Oh, yeah.
And if that's the case, how long could you be? People have, I'm sure, have done that calculation. It's something like 1.5 liters of water, like a liter of water, if you lined up all of those molecules, would be like a light year.
Wow. I'd be quite long.
Yeah.
I guess it depends how hydrated
We would be.
I am.
I think, I'm just going to put this out there as a guess. Other people should check me. This is my very quick mental math. I'd say that we could be as big as the galaxy if you just stretched out all of our atoms.
Would that be fun? Would I have a good time? Okay.
Having pretended to be something as big as the galaxy for 2 years, I think it would be fun.
So you get it. Yeah.
Yeah, I get it. Yes, so you get really stretched out, or perhaps really tiny. I don't remember which way it works. But things change. Things that you don't think should change are going to be different if you're moving at very fast speeds. So he thinks about this. For 10 years, Einstein, while working in the patent office without any equipment to run experiments, he just does thought experiments. He's thinking through different scenarios in his head. And after that, he publishes in 1915 his theory of general relativity, which is like special relativity plus acceleration. Because before, he was assuming everything was moving at constant velocities, but that's unrealistic. Things in space are changing velocity all the time. It didn't match Newtonian physics because Newtonian was observing these planets accelerating around on their orbits. And so he did all of these thought experiments that led him to realize that the acceleration we feel every day and the acceleration that the planets undergo, that's just due to gravity. And actually, gravity is not this string connecting us to other things, but it is our motion. It is the consequence of our motion over the fabric of space-time. And the fabric of space-time is bumpy. It has hills, it has valleys. And when you're in a valley, you feel strong acceleration due to gravity. The concept of space-time, by the way, people think that that's something Albert Einstein came up with. No. It was a concept developed by his teacher, Hermann Minkowski, in 1908, 3 years after special relativity was published. Just putting that out there. And now we understand gravity not as this linear straight line force, but as something that acts on curves. And when you feel gravity, it is because you are feeling your motion over curved space-time. What a jump that happened over like 300 years from the planets are stuck in a rigid rotating sphere around Earth to actually we all are on this weird theoretical quantum fabric of space-time. And we're still not done. There are still parts of gravity that we really don't understand. We understand it on most scales. Einstein's theory of relativity, general relativity, works on like 30 orders of magnitude. Everything from like small-ish things here on Earth up to galaxy and galaxy clusters. They operate according to gravity that we understand. But in really extreme conditions, like at the center of a black hole when you reach like infinite density, or on very, very small scales at the quantum level, relativity breaks down. And so we are actively searching for a theory of gravity that can unify these different scales. It would be called the grand unified theory, the gut theory of gravity. And people have attempted to find that. Back in the 70s or 80s, people introduced something called MOND, which was modified MO, Newtonian dynamics. And it was this suite of different hypotheses where they were trying to make gravity act differently on different size scales. And every once in a while you'll see a paper come out that supports this theory, but most of the scientists that I know have disregarded it or have dismissed it. And there are people trying to figure out the quantum nature of gravity. Gravity is such a weird force. It is one of the 4 fundamental forces we've identified. We have a whole episode about it. Go back to that and listen. Potentially there are 5 forces if that's what dark energy ends up being. But of the 4 that we know about, gravity is so fucking weird. It doesn't have a quantum particle to carry the force like all of the others. There are no bosons. There's no force carrier particle that works with gravity to make that information travel. And as far as we know, gravity is the only one of those forces that every single type of matter interacts with. Like dark matter does not interact with light. Or I think the one of the nuclear forces, it just interacts with gravity and the other nuclear force. But why? So gravity is really weird. We're trying to figure it out still, but we understand it well enough to have left our planet surface and launch things into orbit around Earth and the sun, I think. We have understood it well enough to build detectors for gravitational waves. We have tested and proven general relativity over and over again, from observations of solar eclipses to observations of other transits. It really does seem to work in almost every sphere of life, sphere of the universe. Shout out to the ancients. But yeah, that's gravity. And I hope that one day we understand it better. Maybe one day we'll find a graviton. I'm not team graviton, though. Did you have any ideas for a funtivity, or are you?
I would love to talk about your birthday real quick. Okay, Moiya, it is your birthday. If you're going out tonight, what kind of motions are you up to? What are your laws of motion?
What are my laws of motion? You mean like dancing?
Yeah, that. I think also just the way that you interact with the world. What are your...
Ooh. Okay. One law of motion that I follow is that you can be slow or in the way, but not both.
I love that.
Mm-hmm. Especially walking on the streets of New York City. And as I will be doing on my birthday, walking on Bourbon Street, gotta do that. You can be, don't walk slowly in the middle of the street.
I really agree with that. That is the key law, I think, to motion in a city, for sure.
Mm-hmm. Yeah. Okay. So that's Moiya's law of motion number 1. Moiya's law of motion number 2. One rule I have always had in my life, I actually did write in my journal that I kept through middle and high school. I wrote down different laws that I follow, or different rules. Always join in a slow clap.
I love that.
Mm-hmm. Unless it's for obviously gross reasons.
Oh, yeah,
but
of course.
Yeah.
I think a more cynical younger me was always self-conscious to join for some reason. But now I always do it too, and it's fun.
Mm-hmm. Younger me also felt that self-consciousness, I think. And she was like, nip this in the bud.
That's so embarrassing.
Always join. Yeah. Because it does feel silly when you first start. Yeah. You're like, what is the beat here? But no, it's good because you love it at the end. Every time. And then my third and final law of Moiya's law of motion is... I'm just thinking of more pedestrian laws that I have set for myself.
Completely. That is a very impactful way to be, so.
But I do want to have it be a celebratory law for my birthday. And so I want to think about the ways that I use motion to celebrate, move the extremities. When I'm trying to do a celebratory dance, I want to maximize the movement of the parts of my body that are furthest from my core. I'm trying to maximize angular momentum of my body. So just move your feet, move your hands. Don't be afraid to lift your arms above your head. Be a millennial and wave your hands in the air like you just don't care. Show your armpits. It doesn't matter.
I love that.
That's the final rule.
Those are great rules. I think we'd all be living a really happy life if we followed those.
Corinne, do you have any laws of motion? I know it's not your birthday, so you can get one.
Okay, let's see. Mine would be, if we know each other and we're not close friends and you see me at a store, we don't have to catch up. We can both wave and smile and keep moving.
That's so true.
And not even in a grumpy way, but it's like neither of us want to do that.
Right. It's just obligatory if you feel like you have to. With an acquaintance, no. Do the wave, do the nod.
Like, it's great to
go
see
about
you.
your day.
Yeah. And keep moving. And it's always like at Target or something. So
yeah. And you're like, I don't want you to see what type of deodorant I'm buying.
I don't want anyone to see me. Yeah,
Leave me
exactly.
alone.
You didn't see me, actually.
If you saw me at Target, no, you didn't.
No, you didn't. Great. So I think we can all take that into the new year.
Yes. I'll definitely take that into the new year. Thank you for that advice.
Okay, listeners. Well, wherever you're moving today, I hope you remember that you are space.
Yeah, you are.
Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.